So a quick note about equal and equivalent sets. So equal sets are exactly what you think. Two sets are equal exactly when they have the exact same elements in them. One way that mathematicians view it is that they're subsets of each other. A is a subset of B, and B is a subset of A. Everything that's in A is in B, and everything that's in B is in A. A related concept, but not as strong, are equivalent sets. And then all we care about are the number of elements. So if the number of elements of two sets are the same, if they equal, then we'll say that they are equivalent. A is equivalent, that's a little tilde there, B. I do want to talk about this tilde for a second. If you remember from logic, we've used that tilde to mean the negation of something. And just like the English language, there's a lot more concepts than there are symbols to go around. So we're going to have to reuse symbols. It's just part of the game. But you can determine the meaning of the symbol by the context in which it operates. This tilde is between two sets. It's kind of like an equals between two sets. So in this case, it means these sets are equivalent. If it was something like this, if you had a P with a tilde before it, and I said P was some sentence, then you'd say, oh, now we're in the realm of logic. P isn't a set, P is a sentence. So this tilde in front of it means the negation of that statement. The other thing that's different, it's a little more subtle, is this equals here and this equals here. Well, this equals is a set equals. They look the same, of course. But this tells me that these two sets are equal. This equals down here, well, the number of elements of a set, well, that's just a number. So this is just a regular old number equals, or a regular equals. So those equals kind of are referring to two different things. So you can see how there's lots of different symbols around. We just have to be aware of the context in which they operate to determine their meaning, because some of them will get reused. Back to our example. Here are two sets. 1, 2, 3 is the first set. 1, 2, C is the second set. Well, the number of elements in each, well, they each have 3 elements. 1, 2, 3, 1, 2, 3. So, since they have the same number of elements, these sets are equivalent. But they're not equal, since 3 is an element of the left-hand set, but not of the right-hand set. So, since all of the elements of A aren't elements of B, then these aren't equal. You need to have everything in A be in B, and everything that's in B be in A. So they have to have the exact same elements. Here's a 3, here's a C. They can't be the same. An important thing to do with sets is to combine them in ways to make larger or smaller sets that will help you reason and talk about mathematical concepts. So we're going to talk about a few different ways of doing this. In fact, probably the most useful and the most common ways. They are the union and the intersection, which are probably the two most useful. And then we're also going to talk about the idea of a set difference and a complement. So, again, if you notice in the definition of these, we have words like or and and. So the reason that we did logic is that so we can make sense of these definitions and future definitions going forward. These words are very important to us mathematically, so that's why we started going over some logical ideas. All right, so let's talk about the union. Well, the union of two sets, well, it's all elements X where X is an element of A, or X is an element of B. So imagine that these are our two sets. We'll draw a little Venn diagram. We'll take everything that's in A and we'll put it inside of a fence. We'll take everything that's in B and we'll put it inside of another fence. Now we have to have a little overlap here because it's possible that A and B share some elements. Well, the union is everything that's in A or that's in B. So it could be in either set. So the union, I'll do this in blue, A union B, is all of this area. In fact, let me try and shade this in. So it's all of this. So that's the union. It can be an A or B. Once I introduce all these concepts, we'll do a big example with all of them so you can see them with some numbers. Well, the intersection, rather than or, it's an and problem. It needs to be in A and B. So looking at our Venn diagram down here, see if you can identify which area of this Venn diagram would denote being in A and B. And hopefully it's not too hard to see. I'll do this in red. We're doing A and B, so the intersection A intersect B. So the area that's in both is this stuff in the middle here. So that is the intersection. So it needs to be in both A and B. Well, set difference is a little bit different because we're saying it's not in a set. So we needed your elements in the set difference, A minus B, and this minus, this isn't a number minus, this is a set minus since there's sets on either side. So it's all elements that are in the first set and not in the second set. So pause the video, see if you can identify where in our Venn diagram down here where we should shade in. Okay, so hopefully you guys can see, well, we need to be in A, so it's going to be somewhere in this circle because we need to be in A. It says X is in A, but it can't be in B. So we need everything in A that isn't B. So we're going to include all of A except the overlap bit. So let me do this in green here. So it's going to be that bit. I'll shade that in. So that is the set difference A minus B. And I'll just quickly, maybe in yellow, I'll do B minus A. These aren't the same thing. Order matters. Just like in subtraction, order matters. So it's everything in B that isn't in A. Let me shade this in. So there is the set difference B minus A. You can see they are different things. They're not the same set. And then finally we have the idea of a complement. Now a complement is everything not in a certain set. But it makes sense to have limits on that, right? If we're just talking about numbers and I want to say a complement of a set, I don't want to include things like telephones or cats or people or whatever. So when we usually do mathematics, we limit the objects under consideration. We call that the universe. So the universe, and we usually use the notation a capital U for universe, not always, but often we do. And it's just all objects under consideration for our purposes. So the complement is just everything not in the set A, but still in your universe. Really, if you wanted to, I could have drawn universes around all these guys here like this, because we really need to do that when we're talking about sets, since we don't want to let our objects spiral out of control. Sometimes you don't need to specify it. It's not particularly useful, but in this class, especially when it is, I will tell you. Okay. So, we want everything not in A. So, all the objects in A are in this circle. So, the complement is going to be everything outside of it. So, let me do this in blue here. So, the complement of A is everything outside of it. I'm going to highlight this circle, but I'm not going to shade inside of it. I'm going to shade outside of it. So here is the complement. And there are 4 ways of combining sets or dealing with sets to make new sets. We'll do a big example now to get an idea of how to do these with actual elements. Alright, so here's an example with some sets. So our universe, I wrote this in set builder notation, and just to get some practice using our new notation. So it's all natural numbers. Remember, natural numbers are our counting numbers starting from 1. Well, it's all counting numbers such that x is greater than or equal to 1 and less than or equal to 10. So between 1 and 10 inclusive. So that is our universe. That's everything we're considering, just those 10 numbers. I have 3 sets here. A is 1, 3, 7, 10. B are all primes in the universe. And I just want to point out, we'll talk about this later on in the course, but 1 is not a prime number. So I don't want to include 1 in primes. And C is 3, 4, 5, 9, 10. So I'd say pause the video and see if you can work out from the last slide and using those definitions, what, especially if you can do the first 4, what A union B, A intersect C, B minus A, and the complement of C is. See if you can work that out. And then there's a little challenge one here that's kind of combining them all. So it's the complement of A union B minus C. See if you can work that out as well. I'll give you a quick hint. It's a really good idea to change this from a descriptive notation to a list of things. That might help you out a little bit. So pause the video now and try that. Okay, so now that we're back, hopefully you've come to realize that the primes in the set are 2, 3, 5, and 7. All right. So I'll do these without drawing a diagram, but afterwards I'm going to draw a diagram just to see where all these guys live, and that'll move us on to the next topic that has to do with counting. But for now, well, let's just do these. So the intersection is everything in A or B. So we have a 1, a 3, a 7, and a 10. We already have a 3 and a 7 in B, so we don't include them twice. They're already included. But we do have a 2 and a 5. So we have 1. I'll just list them in numerical order, but really, you can list them in any order you want. Remember, order isn't important for a set. So we're going to have 1, 2, 3, no 4, but we do have 5. We don't have 6. We have 7. We don't have 8. We don't have 9, but we have 10. So it's everything that's either in A or B. And maybe I will draw a little Venn diagram here. So in A, we have 1, 3, 7, and 10, but B also has 3 and 7 in it, So those numbers are going to appear in the intersection. And then we have 1 and 10 here. And over in B, we have a 2 and a 5. So that is A union B. So it's everything in those sets. A intersect C is everything that's in common with both A and C. It needs to be in A and it needs to be in C. So 1 is in A, but it's not in C. 3 is in C, so we'll include 3. 7 is not in C, but 10 is in C. So 3 and 10 is the intersection. So maybe I'll just do this one again really quick. So we have A and C, sorry. A and C. So in the intersection we have a 3 and a 10, and here we're going to have a 1 and a 7, and over here we're going to have a 4, a 5, and a 9. So that's how the Venn diagram for just those two sets looks. B minus A, well, that's going to be everything in B that isn't in A. So we look at everything in B, 2, 3, 5, 7. 2 is in B, it's not in A, so we're going to include that. 3 is in B, but it's also in A, so we're not going to include 3. Because remember, the set minus means it's in B, but not A. So 3 doesn't belong in our set minus. 5 is in B, but it's not in A, so we're going to include 5. But 7 is in both. 7 is in B and A, so we're not going to include 7. So it's just these two guys. Maybe I'll highlight over here. So the area that is B minus A is this area here in blue. So this is B minus A. That's 2 and 5. And, well, the complement of C, well, that's everything that's not in C, but still in our universe. So C has 3, 4, 5, 9, and 10. It doesn't have 1, 2, 6, 7, and 8. So it's everything not in C, but of course, still in our universe. And then 5, well, we have to do a little bit of a calculation here. So let's figure out what B minus C is. I'm going to do this very quickly. So B minus C, we want everything in B that isn't in C. So B minus C is going to be 2 and 7. Since that's everything that's in B that isn't in C, 3 and 5 are in C, so we don't want to include them. And then we have A union that. So that's going to be everything in either A or this B minus C. So A union B minus C. Well, that's going to be, we have a 1, we have a 2, we have a 3, we have a 7, and we have a 10. So that's everything that's either in A or B minus C. And now we just want the complement of that. So the complement of A union B minus C is everything in the universe that's not in that set. So that's going to be 4, 5, 6, 8, and 9. So the other numbers from 1 to 10. So there we go. Now, quickly, just to draw this in terms of a Venn diagram, here's our universe here. And we have 3 sets going around, so we can draw one of these triple Venn diagrams. This will be A, B, and C. So let's just go through and put all of the numbers where they go. So 1 is an A, but it's not an either B or C. So I need to put it in the part of the diagram that just puts it in A and not B and C. So that would be there. 2 is just in B, it's not in A or C, so 2 goes here. 3 is in A, B, and C. So since it's in the intersection of all three, I'm going to put it in that bit of the Venn diagram where all three of them meet. 4 is only in C. 4 goes here. 5 is in B and C, but not A. So the area of this Venn diagram, that's B or C, but not A, or sorry, B and C, but not A, is here. So that's the overlap of B and C, but not A. So we'll put 5 here. 6 is in none of these. So 6 lives outside all three circles. 7 is in A and B, but not C. So 7 lives here. 8 is in none of them. 9 is only in C. And 10 is in A and C, but not B. So 10 would live there. So this is how the Venn diagram for these 10 numbers looks, and these sets. So hopefully you get an idea for how intersection, union, set difference, and complements and universes work. The last way of combining two sets that's going to be important to us, and it's going to be important when we talk about multiplication and multiplication-related concepts, is something called a Cartesian product. And it's the way we can take two sets and kind of glom them together to get elements that are kind of these ordered pairs. So here with these round brackets, let me write that a little bit better. Here with these round brackets means order matters. So AB is not the same thing as, I should write BA, not AB again, as BA. So here, order matters. So the way you make these sets, you can think of it like multiplying. What we're doing is we're going to take every element of the first set and combine it with every element of the second set and get every possible combination of an element from your first set and an element from your second set. And a way to think about this, again, you can draw a little diagram like this with one set going horizontally, the other set going vertically, and just write down all possible ordered pairs. So this ordered pair, well, you have 1A, so the one from big A and the little a from big B. Here you have 2A. Here you have 1B. Here you have 2B. Here you have 1C. And here you have 2C. So it's all possible combinations of an element from your first set and an element from your second set written as an ordered pair. So we can list that, in fact, it's just 1A, 1B, 1C, 2A, 2B, and 2C. So that's our Cartesian product. And note, well, A has 2 elements, B has 3 elements, And A times B, and we'll talk about this in the next video, has 6 elements. And that's going to be a pattern that is always going to hold. You can see what we're doing. We're kind of drawing a rectangle that is 2 by 3. So of course there is 2 times 3, 6 little cells here, 6 possible combinations of an element of A and an element of